you'll know that it's kicked around the 1970s, okay, originally written in Fortran. So it goes way, way back. And it's basically a de facto open protocol, okay? It's not an actual system per se. So it's just the same as FTP, HTTP, all the other things. It's an application layer protocol, okay? It sits on top of the physical network and sits on top of all the other stuff. So originally, Modicom PLCs, so Schneider put it together out of the box originally, half duplex at its core, so only one thing talking at a time. Send out a request, get a response back. One thing on the pipe at a time. One master up to 247 slaves. There are variants that have extended the number of slaves, depending on the traffic on your network. I'm pulling a lot of energy metering over ModBus at the moment, and I do not like to put more than about 8 or 9 slaves on a 9600 board network and try and get any sort of sensible fast data out of them. Okay, if you put lots and lots of slaves as a network, it tends to be very slow from a data collection perspective. So bear in mind you're using serial and you can soak up the bandwidth really, really fast. So typically used with a multi-drop bus. So the classic approach is an RS485 multi-drop serial bus. So now OSI-wise, it only uses in ModBus serial layers 2 and layers 7. Okay, so it's that that layer just above the physical. It's that network or the transport layer. Okay, and 7, the application layer. So that's all that the serial ModBus protocol uses. So that means from a physical perspective, you can run it over just about anything you like as long as it manages the communication handling. Okay, so you see it over 232, 432, 485, modems, all sorts of things. It is what's termed asynchronous byte oriented. So it's not locked up, it just sends chunks of data, zeros and ones, as a byte, and it doesn't necessarily need to send them in any particular timing order. So very much asynchronous. The bus can be quiet for a very long time. Okay, there's no timing pulses or lockup or anything else. Okay, it's pretty low tech, pretty simple, and that's both one of its bonuses and one of its annoyances. So PLCs. Now ModBus comes from the PLC world. Okay, so and again, remember, whenever you're thinking about ModBus, cast your mind back to 1970 and the sort of PLCs that were around at that point. Okay, so when we're talking about ModBus, we talk about input and output discretes. So that's your digital inputs and your coil outputs. So it's often referred to in PLC or in ModBus documentation as coils and inputs. All they are is zeros and ones from your I/O. Okay, so basically, drive a coil to drive an output or read an input. So zeros and ones, that's all they are. Excuse me. Input registers. Again, input is all about reading your I/O. So it's taking a 16-bit input. So it might be an A to D, it might be a BCD switch that's being pushed in. Anything that's coming in from an analog type or a 16-bit integer input on the PLC. So again, if you go back, it's sort of, you go to your Allen Bradley PLCs, it's your I:, it's your input. Okay, it's the direct card reading inputs. So you cannot write to these. Okay, they are read only in a PLC space. So your input register is a read-only 16-bit integer. So generally that's coming from the field. Again, depends on the manufacturer and how they've configured it. So likewise, you get an output register. Okay, exactly the same. It's for driving outputs if it's defined that way. Internally, okay, reading the memory. That's what holding registers are about. Okay, that's where the PLC stores something in an integer file, does calcs on it, takes an input, scales it, does calcs on it, sticks it in its memory. Okay, and that's the holding register read function for ModBus. And again, you can write back to that. Okay, so you can write to the memory of the PLC. So these are the terms you'll see when we're pulling and pushing data to and from the slave devices. Okay, so the master is in charge of the polling, and it asks the slave, I want data, or it feeds it down and says, here, store this in your memory. So does that make sense? Everyone's comfortable with those bits? Before I launch on. Input discretes, outputs, coils. Cool. So again, this is the time as we're going through. So if you watch the pre-recording and you had a piece of notepaper and you went, what was he on about at that point? So feel free to fire the questions in as we go through. So, master slave, okay? Very, very simple. Again, it fits straight back into that application approach we've been talking about with everything that sits on the OSI stack at layer 7. Okay, master slave. So, yeah, or client server. So, in the case of ModBus, this size, the master is actually the client from an IP perspective, and the slave is the server. Okay, sometimes it does your head in and makes you think, but from an application perspective, that's what they are. So the ModBus client, okay, so this is your master, requests the information. Indication happens, okay, response occurs, confirmation comes back, okay. Make a note. If you look at your assignment, this may well feature, heads up. Okay, so master slave, fairly simple. So as we work through it, so we look at the standard packets over the network. Okay, it's a serial network. That's what we're talking about for this session. IP, next session. Okay, so your client server initiates a request. So ModBus has a very discrete small set of function codes. So it sends a function code with some data following it, which tells the server what location, how many, a few basic instructions on what's to be done with the function code that's passed over the network. The server over here performs the action that it was asked to do, and then it repeats back what function code it was asked to perform and sends back the information. It may just be that, yep, I've done it, or it may be, if you've asked for input registers, coils, any of those things, sends it back inside the packet here. Okay, so it receives the response. It's a very simple request receive. Okay, so that is at its core all that it does, and we'll see that as it comes through. So when we talk about OSI model and the protocol stack, okay, 7 up here, 1 down here. So there is a bunch of other physical things that you can run it over. It'll work on all sorts of things. You get ModBus Plus and HDLC is another physical network approach. So here we have our master slave and serial, okay, running over 232 or 485. And next week, as we'll see, okay, it sits on the whole stack here. So the application sits on it and feeds it down through their OSI stack all the way down and over Ethernet. So these here are the two variants we're covering. So this is topic 1 and this is topic 2. So it's where it fits into the OSI stack. So we're 7 and 2 here, and here we are 7, 2, 3, 4. I hope we'll get into it at the beginning of next topic. So what does it look like when it heads over the wire? Okay, so how does it bundle it up? So we've talked about very briefly in the server client approach this bit. Okay, and this is called the protocol data unit. So this is the core. This is the little bit that is saying, okay, what am I doing? Am I reading? Am I writing? Where am I doing it? And what did I read? This is the actual ModBus protocol data unit. So it's generated by the application. Okay, so the application data unit, as in all good OSI stuff, adds address and some error checking, okay, and hands it down the stack. So this is the application data unit here, the ADU, that actually goes over the wire. So obviously, if you're sending it out to a slave, you've got to know which one to go to, which of the 247 that you're actually talking to, and you need to make sure that the data arrives as it was expected to be. So when you see these two terms, that's all they refer to. Protocol data unit is the actual function and the data, and the application data unit adds on top of it the addressing and the error checking. So application, there's two types of responses over the network we can get. Okay, query response with polling, hitting a specific slave, okay, and a broadcast. So if you send out to address 00, it's basically here, everyone have this. Okay, no response needed. So these function codes, they tell the slave what to do, okay, and they also tell it where in the memory map to find or deposit the data. So are we reading a status? Are we reading an input? Are we reading a register or a holding register? Okay, so are we writing a coil out? Sorry, coil, it's output. Again, you can read a coil. Okay, you can read what, you know, it's like anything in the PLC. You know, if you turn the output on, you also read what state it's in. So, okay, so that's all the function codes do. What to do and where to find it. So remember, cast the mind back to 1970 when these guys were coding it. Okay, the memory of your PLC was divided up into specific register locations. Okay, so this is where the numbering convention for ModBus comes from. Okay, so yeah, each function code. So function code 1 is to read coil status. So we're reading something out of this chunk of the memory in the PLC. And in the original bodycons, this was defined with specific addressing. Okay, so the function codes say, right, function code 1, we're going to read a coil status. We're going to read what status this coil's got. Okay, the addressing starts at the beginning. So that's the first coil status. And then we tell it how many we're going to read. You know, might be 8, might be 10, might be 50. Okay, the maximum read in ModBus, off the top of my head, is 120 of anything. Unless somebody's specifically allowed you to read more. But by default, 120 is the maximum number of things you can read across the network. So 120 coils, 120 input registers, 120 outputs. So this is the coil status. The input status is a separate chunk of memory and is numbered separately, as is the input, as is the holding registers. So where you see the addressing of 30,000-ish and 40,000-ish, it's referring to specific memory locations as originally defined in a Modicon PLC in 1970. So this is why some of the addressing and stuff looks a bit weird. You don't have to stick to those numbers. You can use anything you like, but by convention, most people will go with those sorts of addressings. Okay, so at the application layer, what are the functions we can do? Okay, it's pretty simple. We can read the status of our output. We can turn it on. Okay, we can tell it to change state. We can tell a whole bunch of them to change into whichever state we want. We can feed it, zeros and ones and change a whole bunch of outputs at the same time. We can read the input. Okay, you can't do anything else with it. You can just read it. Okay, we have input registers. So these are the function codes. Okay, so this is the number that you put in that little packet at the front of the protocol data unit to tell the slave what to do. So it says, I want to read input registers. Okay, and I'm going to start at a point in the memory and I want X of them. So again, holding registers, so these are memory locations in the PLC. We're not reading inputs, we're reading memory locations. So we can we can set it, preset it, we can write out to a whole bunch of them, or we can read them. Okay, 3s and 4s, I mainly see those when I'm dealing with ModBus. Okay, read inputs, read memory. Okay, those are the two most common function codes I see. Now, this is the one to get your head around, okay? So these are the function codes over here. You'll note coils are memory location 0 up to 9999, okay? If, depending, you can use in some later versions, they've extended out to a much higher number of coils because processors today are a lot faster. You can deal with a lot more stuff. But, okay, memory location 0 to that is coils. So this is, he says, this chunk of the memory specifically. Okay, inputs is 10,000 up. Okay, 10 to 20 basically. Okay, input registers 30 to 40. Okay, holding registers 40 to 50. So these are the specific absolute PLC memory locations. It's what's called absolute. Okay, so this is the memory location, and you'll notice that from a counting perspective, it is 1 based. The first register that you can read in that space is register 1. Okay, now just to do your head in, the protocol is 0 based. Okay, and that's termed the relative address in the Modbus protocol space. It is 0 based. So if you are using a 0 in the Modbus protocol, it will deliver you the first memory location in the PLC. So if you're ever using Modbus and you go, I'm not seeing the number I want, then try adding or subtracting 1 to your memory location and see if you get what you're expecting. Okay? Often people will give you the absolute address, and that doesn't work when you put it into the protocol to read it with a function code. Sometimes they will give you the relative address and you just put it in and it works. Sometimes the people writing the documentation confused and give you one of them and mean the other. Okay, so I have had instances where it's been, I've had to add one or take one off depending on how the documentation works. So just be aware, they are different. The absolute address in the PLC is 1 based, and the protocol when you're reading it is 0 based. So you get this problem. Okay, 0 in the protocol means location 1 in the PLC. So hopefully as you're doing the assignment, this will be a bit clearer. We'll have a wee play with that in practical in a moment. So everyone, if you don't fully understand it, at least you're now aware of it. Okay, so does that make some sense, the way I've explained it? Has everyone sort of got their head around the fact that one of them counts from 1, one of them counts from 0? Okay, cool. This is the bit that trips most people in Modbus, is the actual addressing. So what does it look like on the wire? If we dig in and pull up Wireshark and have a look at it in the IP space, or we pull up, as we can do, the comms transport window and the 2 little bits of software you folks will be using, what does it look like? Okay, well, first up we have an address, then we send a function code. So this is 01. Okay, so this is read coils. So that's what function code 1 is. And then we say, okay, we want it from memory location 0A. Now it's in hex, so A is 10, obviously. So we want location 10, protocol location 10. Okay, so, and we want 2 points. Okay, so we want 2 coils. Tell me about 2 coils, and here's a standard CRC. So down at the bottom, okay, it mirrors back the address, 01. Sorry, the address that says I'm 1. Okay, function code 1 is what you asked me for. There is 1 byte, okay, 1 byte of data, and then the coil data, 03. So if you look at binary, okay, 03 is 1, 1. Okay, so that's what's in the least significant byte. So we asked for 2 coils, so this is telling us that the coils are both on. Okay, so that's what it looks like on the wire. So we'll look at a couple of these. Okay, read the digital input status. Asking for slave 1, function code 2. Okay, we are reading 0. We're reading the first memory location. Okay, and we want 2 points. So this is absolute addresses 1 and 2 in the PLC, okay, reading from protocol address 0. So I was number 1. You asked me for a function code of 2. There is 1 byte, okay, 1 byte of data, and here it is. We've got 2. So we know that the first 2 inputs are in a state of 0 and 1 because that is a binary 2. Okay, so 0 and 1. So that's what the response over the wire looks like. We'll dig into this in a minute. Come on. Holding registers. Okay. Again, we have address function code mirrored back. We've asked it to start at 2. So this is absolute address 3 in the PLC. Okay. We've asked it to bring back one 16-bit integer. Okay, so it tells us there is 2 bytes, and here's the content of our 16-bit integer. Okay, so hex is 4 bits, so there's your 8-bit boundary. So if you add that up, do the numbers, okay, you can put the binary stream underneath it. There is your 16-bit integer, so 2 bytes. So 16 bits. So that is in standard integer format. Okay, again, input registers, function code 4. Okay, so 3 and 4 are the most common reads that I have seen in my dealings with ModBus. So again, start at 0, absolute address 1. Okay, 1 register, and that is what came back in it. Okay, so you look at that, all 1s and 3, so that's 1, 1. So all 1s for the first 8, 9, 10 bytes. Okay, so whatever that translates to in decimal is what was in the register. Or again, okay, it's an input register. So if this was a 16-bit input card with discretes coming into it, then it's telling you that the low 10 are on. Okay, so again, it's all about understanding what that register represents inside the PLC or the device that you're communicating with. Because it may not be a PLC. I mean, I'm using ModBus to talk to energy meters. Okay, so that could well be, an indication of the voltage. Okay, or the accumulated kilowatt hours. And again, one of the other things I'm picking up at the moment is a digital input unit out there on ModBus, and it's actually got a pulsing water meter coming into it. So the input's just telling me if I've got a pulse or not, and then that's accumulating into an internal holding register that I read the count off. So, okay, I can read the input direct, and it will tell me if there's a pulse there at the moment or not, or I can read the holding register, which tells me how many pulses the device has seen. So, loopback test. Okay, this is for getting info over the wire and doing a quick check. Okay, so hit address, function code 8, and it responds. Okay, and says yes, I'm alive, I'm on the network. So the equivalent of ping for ModBus. Okay, that's all it is. Loopback test. Send back the same thing. Okay, I've asked you, are you there? Yes, I am. Okay, so this will work even if you get your addressing wrong. Okay, because in ModBus, I've had devices out there where if you don't ask it for exactly the right function from exactly the right address, it won't even respond. It just ignores you. Okay, so it's an EDMI electrical meter. So